Take an ordinary water pipe, flowing full. Now open a valve and let compressed air force its way in. Within seconds the flow stops behaving like one fluid. It reorganizes itself into a train of gas pockets, called slugs, punching through the liquid one after another. This pattern is called slug flow, and once you know it you see it everywhere. Crude oil risers on the sea floor. Steam boilers. Geothermal wells. Even the frother on a coffee machine. Multiphase flow runs half of heavy industry, and today we are going to simulate it, from scratch. Here is the promise. No black box. Every equation is derived on screen before it becomes code. Every line of Python is short enough to read aloud. And at the end we do not just admire the pictures. We verify mass conservation down to machine precision, 10 to the power minus 15, and the code itself asserts it. Before we write any mathematics, we need a mental map. When gas and liquid share one pipe, what shapes can the mixture actually take? It turns out there is a small family of patterns, and which one you get depends on how fast each phase is moving. At low gas rates, the gas rides as small dispersed bubbles, carried along by the liquid. Push more gas in and those bubbles collide and merge until they span nearly the whole pipe. That is slug flow. Slow everything down instead, and gravity gets time to act, liquid settles to the bottom, gas rides on top, stratified flow. And at very high gas velocity the core hollows out completely, smearing the liquid into a thin film on the wall. Annular flow. Engineers organize this zoo on a flow regime map. Across the bottom, the superficial gas velocity, which means the velocity the gas would have if it flowed through the pipe alone. Up the side, the same idea for the liquid. Every operating point of every pipeline lands somewhere on this chart. Today we live in the slug region, and we choose it deliberately, because those alternating heavy and light pockets hammer pipe bends and supports. Slug flow is the regime that shakes pipelines apart. Now the physics. And we start honest, with the full machinery that researchers actually use, the two-fluid model. In the two-fluid model, each phase K, gas or liquid, carries its own complete set of variables. Its own volume fraction alpha. Its own density. Its own velocity field. You write one continuity equation per phase, one momentum equation per phase, and then couple them through transfer terms at the interface. That is 6 coupled equations before you have discretest anything. Powerful and brutal for a first solver. So we simplify, but we do it in the open, with one clearly stated assumption. In well-mixed slug flow the gas and the liquid travel at nearly the same speed. The slip between them is small. So let both phases share one single velocity field. This is the homogeneous model, and it is the standard first run on the multiphase ladder. Under that single assumption the model collapses beautifully. First, the gas fraction alpha is simply carried along by the flow. A pure advection equation. If you can transport alpha, you contract the slugs. Second, the mixture density and viscosity become volume-weighted averages of the two phases. Where alpha is 1 you have gas properties, where alpha is 0, liquid, and in between, a smooth blend. And third, the pressure drop that drives the whole flow obeys the Darcy-Weisbach law, exactly the one you know from single-phase pipe flow, but evaluated with mixture properties. 3 short lines. That is the complete physics of Part 1. The advection equation is the star of this show. Solve it well, and slugs march down the pipe holding their shape. Solve it carelessly, and your gas quietly leaks out of the universe. Later in this video I will show you exactly how that happens, because it happened to me while building this episode. But what exactly is alpha, physically? The volume of fluid method, VOF, gives the cleanest possible answer. Chop the pipe into cells. In each cell, alpha is a single number between 0 and 1, the fraction of that cell's volume currently occupied by gas. Alpha equals 0, pure liquid, shown teal. Alpha equals 1, pure gas, gold. Now read across this row, 0, 0, a sliver of gas, mostly gas, pure gas, and back down to liquid again. That is a slug, expressed as arithmetic. Notice what we did not do. We never drew the interface, and we never track it explicitly at all. We only transport the field alpha, and the interface is simply wherever alpha crosses 1/2. Those partially filled cells at the nose and the tail are where it lives. This same idea, in 3 dimensions with a sharper transport scheme, is the heart of interfoam, the open foam solver industry uses for sloshing tanks and breaking waves. Understand this row of 9 cells and you understand the heart of that too. Time to turn calculus into arithmetic. We discretise the advection equation on our grid of cells. Our flow moves left to right, so information travels left to right. Whatever cell I is about to become, it is becoming because of what is arriving from upstream, from cell I-1. The upwind scheme takes that literally. The new alpha in cell I equals the old value, minus C times the difference between cell I and its upwind neighbor. C is the Courant number, the fraction of one cell that the flow crosses in one time step. And that gives stability a physical meaning. If C exceeds 1, the flow jumps across more than a whole cell in a single step, the scheme loses track of where its information came from, and the solution explodes. Keep C at or below 1, the Courant-Friedrichs-Lewis condition, and upwind is rock solid. We run at C equal to 0.9. Now the trap I promised, and it is a real bug from building this very solver. The naive inlet condition simply stamps the inlet value into the first cell. It looks reasonable. It runs. And it silently creates gas out of nothing, because that first cell just changed without any flux delivering the change. My mass balance was off at the 4th decimal place, and nothing crashed to warn me. The fix is a ghost cell. Pretend there is one extra cell just upstream of the inlet, holding the inlet value, and update cell 0 with the very same flux rule as every other cell. Same 3 lines of code, different shape. The conservation error falls from 10 to the -4 to 10 to the -15. That is not an improvement. That is a different category of correct. Now we write it. 7 steps. And every line you are about to see runs unmodified in the file you can download, so the video and the code can never drift apart. Step 1, Geometry and Grid. 10 meters of 5 centimeter pipe, chopped into 400 cells. Numpy's linspace hands us the cell positions, the spacing dx falls out of the first 2, and the flow area comes from the diameter. 3 lines, and the domain exists. Step 2, the fluids and the forcing. Water at 998 kilograms per cubic meter. And look carefully at the air density. 1.02, not 1.2, because this channel broadcasts from Kathmandu at 86 kilopascals, and your simulation should respect your altitude too. The inlet function feeds a square wave, gas for the first 1.2 meters of every 3 meter period, liquid for the rest. A slug train, in 3 lines. Step 3, the mixture laws we derived earlier, transcribed exactly. Volume-weighted density, volume-weighted viscosity. When the derivation is honest, the code is boring. And boring code is correct code. Step 4, the velocity, and here is the subtlety. Friction depends on the Reynolds number, but Reynolds depends on the velocity we are trying to find. Chicken and egg. So we iterate, guess you, compute Reynolds, get the friction factor from Holland's explicit formula, solve Darcy-Weisbach for a better you, repeat. It converges in a handful of passes to 1.207 meters per second. Step 5, the conservative upwind update, ghost cell included. These are the exact 3 lines from the previous scene, with number py slicing updating all 400 cells at once. This is the entire numerical scheme. No solver library. No hidden machinery. Step 6, march in time. Every step asks the inlet what is coming in, logs the liquid volume actually crossing each boundary, and that running total is our audit trail. Then it applies the upwind update and advances the clock. 1100 steps, sweeping the pipe 2.5 times over. Step 7, the audit itself, and the sentence this channel is built on. Verify, or it did not happen. The change in liquid volume must equal the net inflow. Our discrepancy, 1.8 times 10 to the minus 15. Floating point round off, asserted in code, so this script fails loudly if it ever degrades. Here is the moment this whole episode has been building toward. What you are watching is not an animation I drew by hand. It is the alpha field the solver computed, mapped cell by cell into this three-dimensional pipe. Gold wherever alpha exceeds 1/2. Teal elsewhere. The pipe starts completely full of liquid. Now watch the inlet on the left. The first gas slug enters, exactly 1.2 meters long, and marches downstream at the mixture velocity we computed, 1.2 meters per second. Behind it comes the next slug, 3 meters later, precisely on the schedule the inlet function promised. Now look closely at the slug noses, the front edge of each gold pocket. They are softening as they travel. That blur is numerical diffusion. It is not physics. It is the price first-order upwind charges for its stability, and it grows a little with every single time step. This is the honest trade-off at the heart of CFD, stability against sharpness. First-order upwind never oscillates and never blows up, but it pays for that safety by diffusing every front it carries. Fixing it is exactly where part 2 begins. A result without a check is a rumor. So before anyone celebrates, 2 independent checks. 1 physical. 1 mathematical. Check 1 is physical, liquid holdup, meaning the fraction of the pipe volume occupied by liquid at each instant. We start with a pipe full of liquid, so holdup begins at exactly 1. As the slug train fills the domain, holdup must fall and then settle around 1 minus the mean inlet gas fraction. Our inlet feeds gas 40% of the time, so the target is 0.6, the gold line. And the computed curve does exactly that, oscillating around the target as each slug enters and leaves. The physics answers back correctly. Check 2 is mathematical, the volume audit from step 7. The change in liquid volume inside the pipe, against the net liquid volume that actually flowed in, integrated over all 1100 time steps. Relative error, 1.8 times 10 to the minus 15. That is floating point round off. The scheme is conservative not approximately, but exactly, by construction. 2 checks, 2 passes, 0 hand waving. Let us take stock of what we actually built in one sitting. We read a flow regime map. We collapsed the 2-fluid model down to the homogeneous model with one stated assumption. We met the volume of fluid field alpha. We discretisted with a conservative upwind scheme, stepped around a real conservation bud using a ghost cell, wrote the whole solver in 7 short steps, watched its own output travel down a 3-dimensional pipe, and proved to 15 decimal places that not one drop of virtual liquid went missing. Next time, we kill the smearing. TBD limiters, how to keep upwind's bulletproof stability while making those slug fronts razor sharp again. The complete solver, and the derivation PDF with every step of today's algebra, live in the flow from scratch pack linked below. If deriving things before trusting them is your kind of engineering, subscribe. See you in part 2. Let us take